We are live, all right. So we are very lucky today to have Dr. Leslie Rogers. She got her BS in Physics and Mathematics from the University of Ottawa in Canada. She has her PhD in Physics from MIT, and she is currently a Hubble postdoctoral fellow at Caltech. She has done a remarkable amount of other sort of graduate research and postdoctoral research at MIT as well. So we're very lucky to have her. Our seminar series is supported by a grant from the University of Central Arkansas Foundation and the Department of Physics and Astronomy at UCA. If we have any questions for our seminar speaker, please use the hashtag GHO seminar, and I will follow those on Twitter, or if you have a question here locally, just holler it out, and she'll be happy to answer it. So I'm going to dim the lights. Go ahead, take it away, Dr. Rogers. Thank you for being here.
Great, it's my pleasure. Here, just let me take a second to share my screen. Okay. So can you now see my slides?
Yes.
Okay. I'm getting a fair bit of an echo. Hopefully that'll be okay. But can you hear me okay still?
Yes, we can hear you great.
Okay, perfect. So I'm delighted to be here today to tell you a bit about the diversity and demographics of distant rocky worlds. And I guess I should update my CV and website. I recently moved to UC Berkeley, actually, as a Sagan Fellow. So I'm no longer at Caltech. My website's a little out of date, but I haven't been at Berkeley that long. And actually, next September, I'll be moving to the University of Chicago to start as a professor there. So
wow, that's awesome.
Yeah, I'm looking forward to it. Okay, great. So let me dive in then. So we now know that when you look up at the sky, pretty much every star that you see is orbited by planets. And these planets orbiting other stars outside our solar system are called exoplanets. Now, there have been many thousands of exoplanets discovered to date. And this is what I'm showing here in this diagram, where on the horizontal axis, we have orbital separation in astronomical units. Can you see my cursor when I use it to point?
Yes, we do.
Oh, okay, wonderful. And then on the vertical axis, we have planet mass and Earth masses. And each one of these dots represents a planet that's been discovered. So there have been many thousands of planets and exoplanets and planet candidates discovered to date by several different detection techniques that I'll review in a bit more detail in a little bit. Right now, I just want to emphasize that there's a tremendous diversity among the planets discovered to date. Everything from planets that are sub-Earth sized to planets that are a few times the size of Jupiter. We found everything from planets that are orbiting their host stars within a matter of hours, almost skimming the surface of their host stars, to planets on very distant orbits, or planets that are untethered to a host star at all. And so, from among this tremendous diversity of exoplanets discovered to date, in my talk today, I'm going to focus in particular on rocky exoplanets. And I don't mean to say that kind of gas giants or ice giants aren't fascinating or interesting or important. They certainly are. I love Neptunes and Jupiters as well as rocky planets. Nor do I mean to imply that rocky planets are the only places that potentially life could evolve. But perhaps they provide the most familiar environments that we could visit with our imaginations, if not our interplanetary spacecraft. So in my talk today, I'll focus on three main questions related to rocky exoplanets and give you essentially the current empirical constraints on each of these questions. So the first are, how common are these small exoplanets? Are rocky planets rare, or are they very abundant? The second question, which planets are rocky? And finally, how Earth-like are these rocky exoplanets that we're starting to discover and to characterize? Okay, so let me get started with the first question. How common are small exoplanets? And for that, I'll begin by reviewing some of the detection techniques used to discover and to characterize exoplanets. Now, first, I want to emphasize that discovering an exoplanet is not as easy as going to a telescope, opening the dome, and opening the shutter and taking a picture. Direct imaging of a planet is very challenging, and it's not necessarily because a planet itself is so faint, but rather that you have this little planet hidden in the glare of its host star, which is typically millions to billions of times brighter. So it's mostly an issue of the contrast ratio that you need to achieve to try to image that planet. So by analogy, you can think of directly imaging an Earth or a Jupiter-like planet to be analogous to trying to see a firefly within the glare of a huge bright searchlight in San Francisco from Boston on a foggy night. So it's a tremendously challenging thing. And actually for this National Geographic article, they were trying to get a picture of the firefly, but of course couldn't because of this issue of contrast ratio. So this little guy is actually photoshopped here. Despite these tremendous challenges, direct imaging of planets has been achieved in some spectacular cases. Here's an example of the HR 8799 system. So here you can see this image of these 4 planets here, lettered B, C, D, and E, orbiting this nearby young aspectral type star. And the reason why the star looks so funny is because essentially they've blocked out as much of the starlight from the central host star as they can. But as you can see, based on the scale of this image, where this bar is 20 AU, and an AU is the distance from the Earth to the sun, this technique is mostly sensitive to planets on very long period orbits that are widely separated from their host stars. And it's also mostly sensitive to massive self-luminous planets. So these are all Jupiter mass planets, and these planets are very young. So we can see their bright thermal emission. So though this is a path forward that NASA will be pursuing in the coming decades to try to discover and characterize Earth-like planets, with current technology, we're not yet at the point of characterizing rocky exoplanets with direct imaging. So for the sorry, is there a question?
Nope.
Okay, let me continue. So for the purposes of my talk today, I'll mostly be focusing on planets that have been discovered by 2 different indirect techniques. And so let me describe these briefly to you now. So the first one of the most prolific techniques to discover exoplanets is by using stellar wobble, or this is also called the radial velocity technique. So you might be familiar from your studies of mechanics or orbital mechanics or Kepler's laws that when a planet orbits a star, really it's not just the planet going around the star, but the star and the planet orbit their common center of mass. So as the planet orbits around the star is actually moving around in its own little orbit as well. And so the motion of the host star is imprinted on the host star's spectrum by this periodic red shift and blue shift. So as the host star is moving towards us, the light from the star will be Doppler shifted to the blue, and when the star is moving away, the light will be Doppler shifted to the red. So astronomers can get spectra of the host star separated in time and essentially watch the lines be red shifted and blue shifted to measure kind of the motion of the host star and infer the presence of a planet. So the more massive a planet is, the stronger it'll tug the host star and the larger the motion will be. And the current state of the art is to measure this radial velocity, or the stellar wobble, to a precision of 1 meter per second. So that's essentially a comfortable walking pace that astronomers are measuring the motion of these stars several light years away. So I find that pretty incredible. Okay, so the stellar wobble is the first main technique that I'll be presenting data to you from today. The second is transits. So if a planet's orbit is serendipitously aligned with respect to our line of sight here on Earth, then the planet might pass in front of the disk of the star, blocking some of the light headed our way to our telescopes here on Earth. And so for measuring the brightness, if we're monitoring the brightness of the star, essentially we'll see the brightness dip by 1%, in the case of a Jupiter passing in front of the sun, or 0.01% in the case of the Earth passing in front of the sun, for a duration of around a few hours. And so by monitoring the brightness of these distant stars and watching essentially for the stars to blink at us, astronomers can discover planets transiting their stars and also get a measure of the planet's size relative to the size of the host star. Okay, so here's the star field that I started with. And actually, this isn't just a random patch of the night sky. I chose this in particular. I'm not sure if anyone there can recognize this constellation. But in fact, this is the constellation Pegasus. And I chose this specifically because in this star field, there's the first ever discovered directly imaged planet system, HR 8799, as well as the first radial velocity planet ever discovered, 51 Peg, as well as the first transiting planet, HD 209458b. Now, all these firsts were essentially Jupiter-sized, Jupiter mass planets, but the radial velocity and transit techniques are sensitive to smaller, potentially rocky planets. And they've been finding these smaller planets in abundance. So now let me come back to this question of how common are these small planets that are potentially rocky? And well, to address that question, we can look to the results of the Kepler mission, which is the current record holder mission that has discovered and confirmed more planet candidates and planets than any other. So the Kepler mission essentially consisted of a spacecraft that stared towards a single patch of the sky, monitoring the brightness of all told around 200,000 stars for a baseline of around 4 years. And so Kepler has discovered now thousands of planets. And so it forms, that data set is really the best constraints that we have to date on the occurrence rates of small planets. And so here's a summary of some results from the Kepler mission. So in this histogram, essentially what I'm plotting is planet size on the horizontal axis, and then the fraction of stars with planets on orbital periods between 5 and 100 days on as the vertical axis. And this is a figure from a paper by Pettigrew et al. And this is based on Kepler statistics. And so here you can see clearly that essentially the occurrence rate, at least on these close-in orbits, increases substantially as you move towards smaller and smaller planet radii. Based on these numbers, essentially, planets smaller than Neptune, smaller than 4 Earth radii, are more than a factor of 10 more common than planets larger than Neptune. And in fact, if you add up these 4 bars in this plot corresponding to the planet smaller than Neptune, you find that roughly 50% of stars like our sun host a planet between 1 and 4 Earth radii. Again, in this range of orbital periods between 5 and 100 days. So clearly these sub-Neptune-sized planets are very common. So these results were from the Kepler Transit Survey, but actually, essentially in every planet survey or planet search that has been performed, they've found increasing occurrence rates of small planets as you move to smaller planet sizes or planet masses. So the results from Kepler are consistent with previous radial velocity searches of planets, and also microlensing, which is a technique I won't be focusing on today. Okay, so in response to this first question that we set out to answer today, how common are small exoplanets? Well, based on the results of Pettigrew et al. From the Kepler mission, we saw that roughly 50% of stars, like our sun, have planets smaller than Neptune, with orbital periods between 5 and 100 days. Okay, so now among these planets between 1 and 4 Earth radii, which of those might be rocky? So in the solar system, there's this order of magnitude gap in mass between the rocky planets, the largest of which is the Earth at 1 Earth mass, 1 Earth radius, and the ice giants Uranus and Neptune, with masses of 15 and 17 Earth masses. And so now, as we saw from Kepler, among other stars, we're filling in this gap in mass. And so are these sub-Neptune, super Earth-sized exoplanets scaled up rocky planets, scaled down mini Neptunes, or something completely different? This is an important question because for many of the planets discovered by Kepler, we just have a planet radius. And so we'd love to know, what is the fraction of planets that are rocky at a given planet size? So when Kepler sees, say, a 1.6 Earth radius planet in the habitable zone of its host star, where it might have surface temperatures that are amenable to liquid water oceans, is that planet likely to be rocky with its transit radius defined by a rocky surface? Or is that planet volatile rich with an extended gas envelope that's contributing to its planet radius? What about a 1.5 Earth radius planet or a 1 Earth radius planet? How likely are they to be rocky or volatile rich? Well, to address this question, we can look to the valuable subset of exoplanets that are detected both in transit and with a radial velocity technique. Because with a planet radius measured from the transit depth and the planet mass measured from the radial velocity amplitude, these together combine to give the mean planet density, and that gives us some handle on a planet's bulk composition. So here I'm showing a planet mass radius diagram where planet mass and Earth masses is on the horizontal axis and planet radii and Earth radii is on the vertical axis. And each of these colored curves are theoretical mass radius relationships for hypothetical constant planet compositions. So the solid blue, red, and magenta curves are for hypothetical pure water, pure silicate rock, and pure iron planets, respectively. And so these curves take into account the compression of various materials as a function of pressure. So as you add more mass to a planet, the pressure gets higher in the planet's interior and the material gets more compressed. Okay, and these solid triangles are essentially the solar system planets. Now, this is literally what this plot looked like 9 years ago when I first started studying exoplanets. Back then, a transiting sub-Neptune-Size planet was a purely theoretical idea. But of course, in the past decade, planet hunters have been populating this diagram, and the Kepler mission has made a huge contribution to that. Of course, mass and radius isn't all that we know about these planets. We also can infer essentially how strongly irradiated are they by their host stars, because we can characterize the planet host stars to know how much light it's emitting as a function of time, and also from the recurrence of the planet transits, we get a very precise measure of the planet's orbital period. So from Kepler's third law, we can know how far away is the planet from its host star, and thus how much light as a function of time is the planet receiving from its host star. So this is what I'm showing here now as the color of each point. So here the color bar is giving the amount of irradiation each planet is receiving from its host star relative to the irradiation that our Earth is receiving from its sun on a log scale. And just from this scaling, so 0 here would be would correspond to a planet that's receiving the exact same insolation as the Earth is. And so the fact that this color bar only goes down to 0.5 is essentially showing that every point on this diagram, so every exoplanet for which we have both a mass and radius measurement to date, is more strongly irradiated by its star than the Earth is by our sun. And that's just a symptom of the selection effects and biases in the radial velocity and transit techniques. Essentially, it's much easier to discover planets that are on closer orbits to their host stars. Okay, but now which planets might potentially be rocky? So to address this question, let me draw your attention to this mass-radius relationship for a pure silicate composition. So this is kind of a rather generous upper limit on the radius of a rocky planet at a given mass. So we expect rocky planets to be composed of some combination of iron and silicate rock, like our Earth is. Our Earth has an iron-dominated core accounting for about 32% of its mass, and a silicate mantle accounting for the remaining 68%. And so, considering the extreme, the rather implausible extreme of planets that are 100% silicate mantles, we can get a kind of an upper bound on the size of a rocky planet of a given mass. So planets that are less dense than this dividing line require some sort of extended volatile envelope that contributes to their measured transit radius. So I'm going to call these planets non-rocky, but I want to emphasize rocky material can still contribute to the majority of the planet's mass, but the planet, essentially the radius that we're seeing when the planet passes in front of its host star is instead defined by some sort of extended gas envelope as opposed to a rocky surface. Whereas planets that are more dense than this 100% pure silicate composition could be potentially comprised of a combination of iron and silicates alone. So here I'll call this regime potentially rocky. Now, you might already be able to see by eye the fact that these mass radius points of all the exoplanets observed to date, they kind of follow this general kind of a trend here. And there's kind of, in this lower right-hand corner, there's a paucity of planets. Essentially, we haven't been discovering very massive planets that are sufficiently dense to lie in this potentially rocky regime. So the fact that these noisy exoplanet mass radius measurements have not spilled over into this high mass, high density regime actually places some constraints on this question that we wanted to address. How does the fraction of planets that are sufficiently dense to be rocky vary with planet size? So one of the things I worked on in collaboration with the Kepler team and observers performing kind of radio velocity follow-up of Kepler discoveries was to explore how does the sample of Kepler planets with Keck-Hyra's radio velocity follow-up constrain the fraction of planets that are sufficiently dense to be rocky as a function of planet size. And so essentially a lot of statistics went into this. I'll just skip to the main results and show you kind of what we found. So here's a summary of some of my results. And so on this plot, I'm showing planet radius on the horizontal axis, and then the fraction of planets of a given size that are rocky on this vertical axis. And essentially the color shading of the points is telling us how likely a given value of F rocky is for a given planet size. So let me walk you through how to read this plot. So say you're interested in planets of a given size, say 2 Earth radii. then you look at a vertical slice through this diagram. Values of F Rocky that are shaded red are more strongly favored by the sample of planet mass radius measurements that we have in hand to date, whereas values that are shaded deep blue are essentially ruled out. And so this dark blue corner in the upper right of this plot is essentially showing how we've ruled out the possibility that the majority of 2 Earth radii planets are rocky, or the majority of 2.5 Earth radii planets are rocky. Or essentially, by the time you get to 1.6 Earth radii, fewer than 50% of planets are sufficiently dense to be rocky, at least on this range of orbital periods that probed by the radial velocity and transit techniques. Okay, so this, and that's actually the main takeaway point that I want you to take away from that particular plot, is that most 1.6 Earth radii planets are not rocky. And essentially, you could pick any planet radius larger than 1.6 Earth radii, and the same statement applies, and we can even place stronger constraints on the fraction of larger planets that are potentially rocky. So this gives us valuable insights into the nature of the remaining majority of Kepler planets for which we do not have direct constraints on the planet mass. Further, since one of the main goals of the Kepler mission was to try to constrain the occurrence rate of Earth-like planets on Earth-like orbits around Sun-like stars, this result helps to motivate an operational definition of Earth-like planets, kind of arguing that if we're truly interested in characterizing the occurrence rates of potentially rocky planets, then we should really be focusing on planets that are smaller than 1.6 Earth radii. Okay, so in response to this question, which planets are rocky? Well, I guess technically I've told you which planets are not rocky, but we can say with strong confidence that most planets larger than 1.6 Earth radii are not rocky, or at least their transit radius is not defined by a rocky surface. Okay, so now, how Earth-like are these rocky exoplanets? Well, this is entirely an open question, and it's an active area of research. I will just partially address it today in my talk. And to give you a partial answer, I'll present a couple of case studies. So the first rocky exoplanet that I would like to present to you is Kepler 36b. So Kepler, the Kepler 36 planetary system consists of 2 sub-Neptune-size planets orbiting a subgiant star. So the host star is very similar to our sun in terms of mass, but it's a bit older. It's around 10 billion years old as opposed to 4.5 billion years old. And the reason why I chose this planetary system from all the possibilities to present to you today is because essentially Kepler 36b, the inner planet in this system, is the rocky exoplanet for which we have the very best constraints on its mass, density, and bulk composition to date. I find it absolutely incredible that the Kepler mission managed to measure the properties of a rocky planet 470 parsecs away, so more than 1,000 light years away, with a precision comparable to that with which we knew the properties of the solar system planets at the turn of the 1900s, before the invention of interplanetary spacecraft and radar ranging. Now, this incredible precision on the measured masses and radii of this planet is a consequence of detectable solar-like oscillations in the planet host star, which allows the host star to be very well characterized, the precise Kepler photometry, as well as measured variations in the planet transit times and dynamical stability considerations. So let me walk you through all the different avenues of information or that give us constraints on the properties of these planets. So Kepler 36b and c were initially discovered in transit in the Kepler data by Josh Carter and collaborators. So here I'm showing you some Kepler photometry. So here's a Kepler time series, kind of zoomed out, giving you a wide range of covering a longer baseline of time here. So each of the little kind of raindrops down here correspond to the planet transits. And here, kind of zooming in on the transits, so this is time since mid-transit, and here a number of transits have been phase folded together. Here you can see the detected transit of Kepler 36b, the inner smaller planet here in blue on the left, and Kepler 36c, the larger, more distant planet here on the right. And so already, you can kind of see by eye, the transit of Kepler 36c is much deeper than that of Kepler 36b by a factor of around I guess it goes like the planet radius squared. And so this is already showing you how that the outer Kepler 36c is a larger planet. And indeed, it has a planet radii of around 4 Earth radii, whereas Kepler 36b's radius is just 1.5 times the size of the Earth. But now, these transits of the various planets don't recur like clockwork. Instead, the planets are dynamically interacting, and the gravitational tugs of each planet on each other causes the planets to sometimes arrive a little bit late to transit their host star, and sometimes a little bit early. And so you can see that visually in this diagram. So here, this is a river plot where each line of pixels essentially corresponds to a transit of one of the planets. So Kepler 36b here on the left and Kepler 36c on the right. So the first row will be the transit, will be the first transit discovered by Kepler, and the later transits are shown at the top. And this is, so the color of each pixel is essentially giving you the apparent brightness of the star measured at that particular time. So these green values are essentially the nominal brightness of the star when there's no planet in front of it, and where the pixels are blue, that's where the planet is in transit, and the apparent brightness of the star is decreased. Now, the horizontal axis here is time modulo the mean orbital period. So if the planets recurred like clockwork, essentially you would just see a vertical blue bar here centered on 0 on both the left and the right-hand side. Instead, you see kind of this anti-correlated sinusoidal pattern. And this is essentially showing you the consequence of the planets trading off energy and angular momentum between each other. Now, this sinusoidal pattern gives you a coupled constraint on the mass and orbital eccentricity of the planets. But you can actually break the degeneracies by looking at this chopping signal. So you might be able to see, here my cursor is pointing at one example, that at some points in the trajectory of this river, there are some abrupt jumps in the transit time of the planet. So here's one. You can see a corresponding kind of chopping signal or discontinuity here in Kepler 36b. Here's another one up here. Those are essentially due to close encounters between the planet, where there's an abrupt kind of interaction between the two planets. And so that the presence of this detectable chopping signal in the data also further helps us to refine the measured masses of these two planets. So instead of just getting some sort of coupled constraint on the planet mass and orbital eccentricity, can actually solve and separate out the individual masses of the planets and eccentricities. Okay, and so I really want to emphasize that these planets are on extremely close orbits. So as you recall, 1 AU is the distance between the Earth and the Sun, and these planets are separated by just 13 thousandths of an AU. So, and indeed, if you were on the surface of Kepler 36b, at closest approach, Kepler 36c would appear to be twice the size of the full moon in the sky. So, and indeed, this planet system is near the limits of dynamical stability. And in fact, when we kind of fit a model, a photodynamical model to the Kepler light curve, kind of with a 4-year baseline, some of the solutions, if we then kind of try to extrapolate forward in time to predict what would happen if we just let the planets go, essentially some of the solutions fall apart, like the planetary system, the planets collide or the planets scatter, or the planet system falls apart within a few billion years. That's not necessarily saying, within a few billion days, sorry. That's not necessarily saying that that's what will happen to Kepler 36b and c. We know that this planet system has survived for 10 billion years, and so it is dynamically stable today. So by ruling out the solutions to the Kepler light curve that are dynamically unstable on short timescales, we can then even further refine the measured masses and radii of the planets. And so this is work done by Kat Deck et al. And so I've been collaborating with Josh Carter and Kat Deck and Jack Lissauer essentially to revisit this record-holding planet system to use the full baseline of Kepler data collected since these initial discovery papers to try to further refine the measured planet masses and radii. And ultimately, we measure the mass of Kepler 36b to within 4.2% relative precision, and the planet radius measured to 1.8% relative uncertainty. So Essentially, Kepler 36b has the best constraints on its mass and density of any likely rocky exoplanet to date. There's one that gives it a run for its money, or that beats it in terms of radius, but in terms of density and mass constraints, Kepler 36b is the record holder. And so I'm plotting essentially the constraints on the masses and radii of Kepler 36c and b here in this mass radius diagram. And as you can see by eye, Kepler 36c has a much lower density than Kepler 36b. So despite them being on such short or closely spaced orbital periods, where Kepler 36b is orbiting its star within 13.8 days and Kepler 36c orbits within 16 days, in contrast, their densities differ by a factor of 8. So Kepler 36c needs to have several percent of its mass in a hydrogen-dominated envelope. So it could be perhaps more accurately described as kind of a sub-Neptune type planet. Whereas you can see by eye on this mass radius diagram that Kepler 36b is very consistent with having an Earth-like bulk composition. But we can do better than that, in fact. So by coupling these mass radius constraints to a model for planet interior structure. So here I considered essentially a model for a rocky planet consisting of an iron core surrounded by a silicate mantle. And essentially, from the mass radius constraints on Kepler 36b derived from the previous slide, you can translate that into kind of constraints on the core mass fraction of Kepler 36b. And here, this kind of histogram is essentially showing the measurement of the iron core mass fraction for Kepler 36b. So we measure a core mass fraction of around 33%, plus or minus 5%. And as I mentioned earlier, the Earth's iron core accounts for roughly 32.5% by mass of the Earth. So Kepler 36b is very consistent with having an Earth-like bulk composition. So Kepler 36b is the rocky exoplanet for which we have the best constraints on its mass and density and bulk composition to date. And it's consistent with having an Earth-like bulk composition. And in fact, here's a somewhat censored mass radius diagram for exoplanets from GHO et al. And here they were just pointing out that if you look at, here they're only plotting the exoplanets that have masses and radii measured to better than 20%. So that's why there are far fewer points on this diagram than in some of the mass radius diagrams that I previously showed. And here they were pointing out that essentially if you look at all the small exoplanets for which we have constraints on the mass and radius to date to within this threshold precision, they're essentially all consistent with having an Earth-like bulk composition. Now, Kepler 36b is the one that we have the best measurements for, but with these error bars and with the sample that we have in hand to date, they're essentially all consistent with having an Earth-like composition. Okay. Now, the second case study that I want to describe is a little planet called KOI 1843.03, and it kind of breaks this trend. It was also discovered in transit and Kepler data. And composition constraints from Rappaport et al. Essentially show that it must be at least as iron-rich as Mercury. So let me, and Mercury is at least, Mercury's core accounts for around 70% of Mercury's mass. So let's dive in and explore this little planet in a bit more detail. So KY 1843.03 is remarkable because it's the exoplanet with the shortest orbital period known to date. It's whizzing around its host star with an orbital period of 4.2 hours. So essentially the duration of my talk today is like 1/4 of a year on KY 1843.03. And so essentially the composition constraints on KY 1843.03, oh, and it's sub-Earth size. It's around 60% the size of the Earth. And the composition constraint on KY 1843.03 essentially stem from this very short orbital period. So you might be familiar with the concept of the Roche limit from consideration of Saturn's rings, for example. But here we can apply it in this context of a rocky planet orbiting its host star. So now let's imagine that we bring a little rocky planet closer and closer orbits to its host star. As it gets closer, it'll be tidally distorted due to the gravity of its host star, essentially because the planet is an extended object and the near side is closer to the host star, so it feels a stronger tug from gravity, whereas the far side is farther from the host star and feels less of a tug from gravity. As a result, these tidal forces tend to distort the planet. Eventually, as the planet gets closer, even closer, these tidal forces can start to overcome the self-gravity of the planet, and the planet will be tidally disrupted. Now, when expressed in this kind of limiting orbital period or orbital separation, where tidal forces begin to overcome the self-gravity of the planet, is called the Roche limit. And when expressed in terms of orbital period, it just depends on the planet density in this way. So, as you can see, since the minimum orbital period varies as planet density to the -1/2 power, more dense planets can survive towards shorter orbital periods. And in fact, the fact that KY 1843.03 survives on an orbital period of 4.2 hours constrains its mean density to be at least 7 grams per centimeter cubed. So for comparison, the mean density of the Earth is around 5.5 grams per centimeter cubed. So this little planet is more dense than the Earth. And that's where the constraint that it must be at least as iron-rich as Mercury comes from. So these initial kind of composition and density constraints were based on rather simplified models. And so actually, Ellen Price, who was an undergrad at Caltech, did her senior thesis with me, modeling the 3D tidal distortion of ultra-short period rocky planets near their Roche limits to try to better constrain the compositions of KY 1843.03 and also further refine the constraints on the Roche limits of ultra-short period rocky planets. So let me just state the reason why this is a bit of a nuanced problem and not that has to be solved numerically with computers is that it's kind of a circular problem, in fact, because if you have some density distribution for the planet, then that affects kind of the gravitational potential energy at each point. And here, since we're really considering 3D planet shapes, it's not like we can apply Gauss's law in a very effective way. You have to actually consider the mass outside any given point within the planet and its contribution to the gravitational potential at a given point. So the density distribution of the planet then affects kind of the gravitational potentials, and then the planet essentially behaves like a fluid and will flow such that the planet's surface reaches an equipotential surface. So then the gravitational potential feeds back on the density distribution. But then you have a new density distribution which will affect the gravitational potential. So it's kind of a circular problem. So, but there are techniques to solve it, and this is what. So Ellen used a relaxation approach for her senior thesis, using realistic equations of state to describe how iron and silicate material, how their densities behave as a function of pressure within the planet interiors. So here I'll just show you kind of a slice through Ellen's grid of simulations. So altogether, she modeled more than 700,000 little ultra-short period planets, considering a wide range of different properties. Here, I'll just show you a slice through her grid where we fix the core mantle boundary pressure at 10 gigapascals and the central pressure at 250 gigapascals. So here, the color shading in this video is giving you the density, and this kind of discontinuity in the color, this is the core mantle boundary. So this is a very extremely iron-rich case. And here we fix the star to be 100 planet radii away from the center of the planet. And once I turn on the video, as the video proceeds, essentially we're going to be dialing up the mass of the host star, dialing down the orbital period of the planet, and you can see the planet become more and more distorted. So roughly the second to last frame in this video corresponds to a potential model for KOI 1843.03. So this planet could be significantly distorted with a 2-to-1 axis ratio between the planet to star line and the perpendicular direction. So now focusing in on the properties of KOI 1843.03. So here we're looking at a slice through Ellen's models, focusing on planets orbiting stars with the same stellar mass as KOI 1843 and with the same transit radius as Kepler, KOI 1843.03. We can explore in this plot essentially the core mass fraction here on the horizontal axis and the orbital period of the planet on the vertical axis. And here these color contours are giving are contours of planet mass. So here a pure silicate planet is on the left-hand side and a pure iron planet is here on the right-hand side. And so as you would expect, as you increase the proportion of the higher density iron material within the planet mass increases. But now it might be a little bit harder to understand why for a fixed planet composition, say 0.6 or a core mass fraction of 0.6, as you go to shorter and shorter orbital periods, you also increase the mass of the planet. Well, that's just because we fix the transit radius of this planet. So, and if you imagine, the transit radius is essentially telling you how much light the planet is blocking as it's in front of the star. So as you go towards shorter and shorter orbital periods, your planet with fixed kind of cross-sectional area or fixed transit radius is getting more and more distorted. So it's getting more and more elongated along the star-planet line, and the volume is getting larger and larger. Essentially, because these planets are so distorted, we can't just say that the planet volume is 4/3 pi transit radius cubed. Instead, the distortion causes the planet volume to deviate significantly from that. And that's why we see essentially these mass contours bending over here. So if we look, oh, and I should say, so this lower left-hand corner that's cut out is essentially the Roche limit. So planets that find themselves down here will be tidally disrupted. If we look at the properties of KOI 1843.03, essentially we find that the planet is, again, based on these more sophisticated models, it still must be very iron rich, at least 63% by mass in iron, and the planet mass must be at least 0.5 Earth masses. Okay, whoops, sorry, let me go back. So in response to this last question, how Earth-like are these rocky exoplanets? Well, I've really just given you two case studies. The Kepler 36b, the rocky exoplanet with the best constraints on its mass, density, and composition, is very consistent with having an Earth-like composition. Whereas the second case study, KOI 1843.03, is kind of the one example we have to date of a potentially iron-rich exomercury analog. Okay, so now we've gone through and addressed each of these three questions. But really, for how Earth-like are rocky exoplanets, for this question, there's far more than just the iron core mass fraction that we'd love to know. In assessing whether a planet is Earth-like, we'd want to know, does it have a magnetic field? Does it have an atmosphere? Are there liquid water oceans? Is it inhabited? Are there shorelines? Are there clouds? What's the composition of the atmosphere? To date, we've really just scratched the surface of this question, and we're just addressing, in fact, whether these rocky exoplanets have rocky surfaces at all. Luckily, we can look to the future to see what we might be able to infer in the coming years. And there's this whole suite of upcoming space-based transit surveys that will discover and characterize many more planets around brighter stars that are more amenable to follow-up observations. And that, combined with ongoing technological developments of radio velocity spectrographs on ground-based telescopes, means that I think we can expect that the mass radius diagram of planets will continue to be populated in the coming years. So I'm really excited about what we'll find as we bring the composition of planets in general, as well as rocky planets, into better focus. And I think we can look forward to deriving even more empirical constraints on the settings of our science fiction stories. Okay, and with that, I'll conclude. So thank you for your attention.
Wow. So, wow, that's fantastic. We'll open it up to questions. Do we have any questions here from our home audience? Lucas, fire away.
So right at the very beginning of your talk, you mentioned that there were exoplanets discovered that were not bound to stars. And
Yeah.
so those sort of just piqued my interest right at the beginning, because how do we really know that they're there? How do we know that they weren't sort of like blips that just kind of passed something like a meteor rather than an exoplanet?
Okay, so let me describe the two different ways that these free-floating planets have been discovered. The first is essentially using direct imaging, but in this case, it's a bit easier because we don't, there's not a nearby host star to dilute the light from the planet. And so in those cases, most of the kind of directly imaged free-floating exoplanets that have been discovered have been found in what are called these nearby moving groups or nearby young associations. So essentially, these are groups of stars that are associated in terms of distance as well as their proper motions on the sky. So you'll see a group of stars that are like a particular distance away and moving all together in a certain direction, and they all have the same age. And so when you find a planet, essentially by kind of deep imaging that shares the same kinematic velocities, then that gives you a constraint on the planet age and some higher confidence that what you're seeing is actually a planet. So for those image planets, then they are reproducible. You can rule out the possibility of cosmic rays or meteors because you can look back another night and see where the planet is and double check that its motion is consistent with being at the distance and location that you would expect the planet to be. The other way that free-floating planets have been discovered is through gravitational microlensing, which was a technique I briefly mentioned but didn't really describe. And that essentially relies on these serendipitous alignments between the a free-floating planet in the foreground and a background source star. And then the free-floating planet gravitationally lenses light from the background source star, causing the background source star to appear magnified. Mm. And so, actually from microlensing, there's a paper that estimates that there's roughly 1.8 free-floating planets per star, so that there may be more free-floating planets than there are stars in the galaxy. It's still a little controversial and still rather uncertain, because there you are really just measuring the duration of these very short duration microlensing events, and there are more things. A fast-moving star could be masquerading as a low-mass planet, for instance. But I think with upcoming surveys like the Kepler microlensing survey and WFIRST, we'll get better constraints for microlensing on the occurrence rate of free-floating planets.
Okay, cool. Charles?
So on your slide where you're showing the Pegasus constellation, I couldn't help notice that the stars that you were pointing out had like radically different names. So I was wondering if you could just briefly talk about how stars are named.
Sure. Okay, so they're named from different catalogs, essentially. So the brightest stars in the sky, like say 51 Peg, that's likely the 51st brightest exoplanet in the Pegasus constellation. So the very bright stars might have some special names like that. the other HR 8799 or HD 189 209 for 58b, those HD signifiers are essentially signifying the various catalogs that have cataloged those stars. So the same star can have multiple different names because it probably appears in multiple different catalogs. And I guess that's perhaps a rather unsatisfying answer to your question, but you can go, there's something called the Sinbad database, actually, where you can write in a star's name and it'll give you all its other names as well as a whole bunch of data on that particular star. So yeah, there are different catalog. For instance, there are variable star catalogs that include stars that pulse and have brightness changes as a function of time, and they follow their own naming conventions. Kepler had its own naming convention for kind of its planet host stars. So like Kepler 36 is the name of the host star for Kepler 36b, but it has a whole bunch of other names as well because it was in prior catalogs before Kepler monitored its brightness and found a planet around it. So essentially the naming of host stars can be a bit of a mess, and there are many redundant names, but it's common in terms of naming planets. Essentially the planets get the name of the host star or whatever preferred name of the host star the planet discoverer wants to use, with a little letter appended at the end. So like Kepler 36b, HR 8799b. Yeah.
When you were talking about the wobble method that's used to detect exoplanets, you said it can also be used to determine their mass. But in order to know the mass of the planet, or in order to figure it out, you have to know the mass of the star. How do you determine the mass of the star?
Yeah, that's an excellent point. So there are essentially two main ways to determine the mass of the star. So one relies on getting a spectrum of the host star so that you can measure from the host star's spectrum essentially the star's temperature and metallicity. And with a constraint on the star's distance, then you can compare to stellar evolution models and see, okay, for a star with this temperature and this luminosity, what range of mass and radius would we expect that star to have based on these models? So that is rather model dependent. But that's perhaps the dominant way that's used to characterize the host star, so that you get some constraint on the host star mass that then translates into a constraint on the planet mass. There are other, so for instance, in the case of Kepler 36 B and C, we have a better constraint on the properties of that host star, because in addition to getting a spectrum of the star, to know its temperature very well, we also, in the Kepler photometry, see these stellar oscillations. And so in the same way that earthquakes here on Earth tell us about the distribution of material or the density within the Earth's interior, these stellar pulsations and stellar quakes tell us about the density distribution within the planet, within the star. And so that allows a kind of astroseismologists to get even more precise constraints on the mass, density, and age of the host star. So the planet host stars that have the best constraints on their mass and radius tend to be those that were detected through, which have kind of astroseismic detections of their pulsations, whereas other stars rely on comparisons to stellar evolution models.
Thank you.
You're welcome.
It's all error propagation, right? You got to
Yeah, it's all error propagation.
now, so that when you go there, you can propagate that uncertainty.
Yeah, and you can only know the properties of the planet as well as you know the properties of the host star. Yeah. So it is, I think the discovery of exoplanets has really led to a resurgence in stellar science as well.
So you showed sort of the future with some new satellites that would be imaging some of these exoplanets. And that we kind of have those to look forward to and the science that they'll be discovering. But with the Kepler data, is there so much there that we'll be able to get many PhD students able to analyze a lot of interesting questions out of that for many years to come? Or does it feel like we really quickly need to have these other satellites so that we can continue working?
Oh, I think the Kepler dataset will continue providing many PhD theses in the times to come, because it is a very rich dataset, and because, so I should say, I mean, it's a valuable dataset, not just for planets, but also for other areas of astronomy as well. And so in addition to following up the planets that Kepler has already detected, which is already several full-time jobs, there are also a number of opportunities for kind of digging deeper into the Kepler data set with more sophisticated data analysis techniques to really try to extract the signals of even smaller and smaller planets from the noise. So the Kepler data set is tremendously rich. It's already revealed a lot of planets. And now I think there's a lot of interest in groups kind of going back to look, okay, can we find planets from single transit events? So all the Kepler, the official kind of Kepler discoveries were constrained. They had to see at least 3 transit signals within the 4-year baseline of the Kepler mission. But if there was a very long period planet that serendipitously was transiting, that could still be there in the data set. It just wouldn't have been flagged as a Kepler planet candidate yet. And so I think there's a lot of interest in that, as well as going back to the pixel level to try to beat down the noise as much as possible with kind of advanced processing techniques. And I should also mention, even though the Kepler spacecraft, 2 of its reaction wheels broke, so it can no longer look at the Kepler field anymore, it's still operating. And it's now called the K2 mission. And it's now looking at a different patch of the sky in the ecliptic plane every 3 months or so. So, and all the data from the original Kepler mission and now from the K2 mission is publicly available. So it is really open to any bright young person who has a brilliant idea of something to do with it. And the K2 mission, since it's looking at a new patch of the sky every 3 months, they're discovering lots of new planets now around bright stars.
This is really exciting, and
Yeah.
exoplanets, it's definitely from when I was an undergraduate. I remember some of the very first super Jupiter type planets being discovered, and the thrill was, oh wow, you know, and
Yeah.
we'll be able to find smaller things. And so now we're at that time. What advice might you give current undergraduates who are interested in this and want to go into this maybe in graduate school? What sort of things should they do as an undergrad, maybe to kind of get ready to go into that field? Maybe what kind of computer programming or other sorts of skill sets that you wouldn't normally get as a pure physics major? What might you advise?
So, so I would say perhaps the most important additional skill sets to get is one, so computer programming is very important, or very helpful in grad school, for sure. So I would definitely list that among the top 2 things to focus on. And then also, just in general, getting some research experience in preparation for applying to grad school. It's very different to work on a more open-ended problem where you don't have the answer in the back of the book, or no one really has the answer, as compared to doing a problem set. And in terms of so that applies essentially to any area that you would like to pursue in grad school. And I don't know if there's anything specific I would recommend in general if someone wants to work to go on in exoplanets. Overall, I think it's valuable to have a breadth of experience as an undergrad, and not to pigeonhole oneself too much when they're first applying to grad school. So I would just say kind of some research experience in general, and in programming, working on programming skills in general. But then, of course, I mean, specific to exoplanets, especially as we start to move from just pure discovery of exoplanets to planet characterization, exoplanets is somewhat, at least the center of mass is shifting a bit from being purely in physics and astronomy to also being partially in planetary science as well. So, so planetary science, I think, as mostly applied physics. So it involves a lot of chemistry and dynamics and pretty much thermodynamics, every area of physics that you could imagine. So, so if someone had an elective, they might consider a planetary science course or some sort of geophysics course. But if not, I think the main things would be to come in with a solid, diverse physics background, some programming skills, and kind of some introduction to research.
Yeah. We always push students to do undergraduate research projects here or to apply for REUs, like research experiences for undergrads. Do you know of any exoplanet REUs there at your institution?
So I'm currently at Berkeley, and I'm less familiar with the programs at Berkeley. So don't interpret my lack of describing programs at Berkeley for being an absence of programs here. But I know at the University of Chicago, there is an REU program in the physics department. And so students could apply through the physics department to do an REU. And I think they're able to work with advisors in the astronomy and astrophysics department. So that would certainly be an option for students who were interested in working on exoplanets at the University of Chicago as a summer REU experience to apply through the physics REU program.
Yeah. Any other questions? Lucas.
So we were talking about the second case study. I don't know if you've seen the movie Interstellar.
Yes, I have.
That is what it reminded me of, is that it was so close, and then like the gravity was distorting the planet. I guess it was. I was trying to imagine what it would be like on that planet, and I thought, with the gravity distortion, it would probably just tear me to pieces anyway. But I mean, so if we were to get a probe there, would it have? Was Interstellar really relatively realistic in that it would distort the time as well as the space of the planet, or would it?
Right, so that's a great question. So I should say, so in the case of Interstellar, where they were kind of orbiting a black hole and worried about tidal forces there and time dilation, there they were really in a strong gravity regime of a black hole. So here, a planet around a star like our sun, or even a star like KOI 1843, we're not in a strong gravity regime. And by strong gravity, the metric there is essentially the ratio between the escape velocity from the body and the speed of light. So, I mean, a black hole is defined by, at the event horizon, the escape velocity is the speed of light. And so outside the event horizon, you're still in the strong gravity regime where like GM over orbital separation divided by c squared is approaching 1. But for a planet around a normal star, that's not the case. You're still in weak gravity. So you don't need to worry. Essentially, general relativistic effects are negligible in that context. And I think your body would still stay intact. You would be fried to a crisp, but your body itself would not. Yeah, essentially, I mean, the surface of the planet could be at the substellar point could be around 2000 Kelvin. So I think you would probably be fried before you would be spaghettified. Yeah.
So I've got a quick question, maybe a little personal, but you went to MIT for your PhD. Did you know right away what you wanted to do, or did you check it out for a few years and then sort of settle into what area you wanted to get your PhD in?
So I did not know exactly what I wanted to do when I went to MIT. So as an undergrad, I had done some research on meteor ablation in the Earth's atmosphere, essentially modeling shooting stars. And so by default, I was placed in the astrophysics division of the physics department at MIT, because I was kind of the best fit for, in terms of the research I had previously done and my interests. However, I really had no idea what I wanted to work on as a grad student. And so in my first year, I was there on a fellowship. And so I had the freedom to work with multiple different research advisors to get a taste of different areas. So in my first year of grad studies, I worked on a project related to gravitational lensing with Saul Rappaport, on cosmology with Max Tegmark, and then on exoplanets with Sarah Seeger. And it wasn't until the end of my first year that I decided, okay, exoplanets are what I want to do.
Cool.
So for me, at least, it was very helpful to have that option to explore different areas and find kind of a research advisor and a research problem that I was really, who I could work very well with, and that I was really, and a problem that I was really interested in.
Right. You know, and I think sometimes students feel like, oh, well, I have to know so that I know where to apply, but you can go and just kind of see what happens. Right?
Yeah, I would recommend, I mean, you don't want to, some of my friends who arrived at MIT were sure, they knew right away going in exactly what they wanted to work on and who they wanted to work with, and dove into their thesis project right away. And that's completely fine. That's another way to do it. No matter what, I would recommend, don't go to a grad school where there's only one person who you could imagine yourself working with. So I chose MIT because I knew they were broadly strong in physics and astrophysics, and there were a number of people there I could have seen myself working with. And I would, so it's fine if you have a more narrow focus going in, but be sure you don't want to be in a position where there's only one person at your grad school that you could foresee working with. And then if that person moves or gets sick or there's some sort of interpersonal conflict, you don't want to be in a situation where you're stuck. And so at Chicago, for instance, in the astronomy and astrophysics department, we encourage students to work on 2 different projects within their first 2 years. So the students are TAing in their first 2 years, and they're supposed to work on 2 different projects with 2 different advisors, ideally on somewhat different topics, although it doesn't always work out that way. But the idea is to give them the chance to really develop some breadth in their first 2 years and figure out before kind of committing to a thesis project and a thesis advisor.
That's a good idea.
Yeah. But each grad program is different.
Do we have any other questions for our speaker? No? Fantastic. This has been very interesting. Thank you very much for your time.
Oh, my pleasure.
Thank you very much. We're going to go ahead and stop the broadcast, but I definitely want to thank you again. This has been very interesting.
Oh, my pleasure. Thanks.
I'll send you a follow-up email tomorrow.
Okay, sounds great. Thank you for having me. Bye.
Bye-bye.